Now let's finally understand the basics of designing a large system and the requirements that we have to satisfy to do so. Now, ultimately, our goal is to design effective systems to solve very, very big problems. And we're especially focused on how to do this in the context of a system design interview. And just like in the real world, in interviews, there's not always a straightforward answer. We have to weigh the trade-offs and figure out which option is the best. Sometimes there's not a perfect solution. We take the option that happens to be better. So system design is not about memorizing a bunch of facts at all. It's really about the thought process. It's about analyzing what improvements can be made and what we have to sacrifice to get those improvements. Now, in system design, things can get very, very complicated. The good thing about system design interviews is you're not expected to know every single detail of every single component. And we're going to go much more in detail throughout the course, but I think it helps to take a step back and realize what we're doing at the high level. No matter how complicated the systems we design get, ultimately we're just moving data around. When we talk about moving data, we already talked about how data moves around in an individual computer from RAM to CPU, from CPU to disk, and back and forth, of course. In larger systems, though, data can actually be moved around between machines that aren't running as a part of the same machine. They could be running in the same data center, or they could be running in different data centers across the entire world. So then, of course, moving data isn't so simple at all. Moving data across a network, from machines that are located on a different side of the world is not so straightforward, but it just boils down to moving data, whether it's from one machine to another or, from one component of a machine to another component of that machine. All these zeros and ones have to move somewhere. It turns out that moving all these zeros and ones isn't always simple. We're also pretty concerned with how we store data. Now, we already talked about how storing data in RAM is different than storing data on disk, because if a computer crashes or has to restart, the data on disk is persisted. We won't lose any of this data. But when you restart a computer, the data stored in RAM is not guaranteed. We won't be able to save this. And this is just one very simple example. Though storing data can get very, very complicated. In the context of data structures and algorithms, we know that storing data in an array is very different from storing data in a binary search tree. One of these is not necessarily better than the other. They're just different. They have different properties. Binary search trees are good for certain things, but arrays are good for other things. Each of these has its own trade-offs. Now, storing data in larger systems actually follows some of the same ideas, but usually we're storing data on databases or maybe blob stores or file systems or distributed file systems or, a bunch of other ways. And each of these ways is not necessarily better than the other. They're just different. They have different trade-offs. We might want to use a database for certain things, but we might want to use a blob store for other things. But all of these different variations and how complicated they can get, it does boil down to the same thing, which is storing data. That's what we're trying to do. We're trying to move data and store data. It could be a massive, massive amount of data, which is ultimately what makes this complicated. If we were just storing a small amount of data, it wouldn't really matter how we store it. But we know large data has to be stored in an efficient way. And this is related again to data structures and algorithms, where we learned how algorithms on different data structures can be more efficient than other algorithms. And that can, be very important when we're dealing with large amounts of data. And lastly, we want to transform data. It wouldn't be fun if we were just moving data and storing it. We also want to be able to manipulate it. For example, given a bunch of application logs data, maybe we want to aggregate all of that data and transform it to get, what percent of these were successful. Basically, maybe these logs are server response logs, and we want to know what percentage of the requests were successful. Maybe that's what these logs are storing. And we also want to know what percent of the requests were failed. So we would take this data as an input and then transform that data to get something more useful, which we actually care about. This is just one example. I'm sure you can think of many more examples where we want to transform a set of data. I mean, these three operations basically encapsulate all of the functionality of most applications anyway, whether you're talking about Twitter or YouTube. It pretty much boils down to these three things. We want to move data around. In the context of YouTube, we want to move videos around or comments around. We want to store data. We want to, of course, store videos efficiently, and we want to transform data, which could mean a lot of things. It could be encoding those videos. It could be aggregating, data. It could be aggregating views of each video and a lot of other types of metrics as well. Typically, it's our application code which handles this portion, the transformation. But when it comes to designing a large application, we want to be very careful with how we design it, because bad design choices in our application architecture are very difficult to correct later. If you write some bad code, you can always fix that code. But if you start with the wrong database, that's not a matter of just fixing your code or refactoring some code. You have to migrate all of that data from your database to another database, and at the same time, you'll also have to rewrite portions of your application. So the idea is that we might not necessarily know how to write every single piece of code when we're designing our application. That's okay, but we should know the general architecture, because we know that design choices are very hard to correct later on. What exactly is a good design? How do we know if our application is designed well? Because like I said, there's not always a correct answer. We have to think in terms of trade-offs. But even then, how do we measure these trade-offs? How do we know if something is good or if something is bad? How do we compare and contrast? Well, one very important measurement we make about a service or application is its availability. And mathematically, this could be represented as the total uptime of our server divided by the uptime plus the downtime. Or you could also rewrite the denominator to just be the total amount of time. I guess this is a slightly more formal way to represent it, but you'll never end up thinking of this equation when you think about availability, because let's rewrite this. Let's say over a day, our application was up for 23 hours out of the total 24 hours of that day. So this would actually become a percentage. That's how we usually talk about availability. So we would say the availability of our service was 96%. That means if users were trying to make a request to our service, which is, let's say, hosted on a single server, that 96% of the time that users were doing that, they got a response. Our service was functioning 96% of the time. Now, of course, when we design a system, we want the availability to be as high as possible, but it's very, very difficult to achieve 100% availability. Theoretically, it's impossible. There could be some natural disaster which destroys our servers, or, does something which maybe takes out somebody's internet. There could be some kind of EMP or war attack that would take down servers. It's impossible to get 100%, but we can get as close as possible. If our service has a 99% uptime, but 1% downtime, and we want to reduce the downtime by a factor of 10, so that means we want to cut the downtime actually to be 0.1%. That's quite a big improvement. But when you look at the uptime would actually be improved to 99.9%. So it seems misleading, but it's actually difficult to make this type of improvement, because this is really a factor of 10 improvement when you look at it from the downtime perspective. But uptime didn't increase by a factor of 10 because, we can't really have higher than 100% availability. It doesn't really make sense. But this is a big jump. Don't let it be misleading. And so that's also why when we talk about availability, we measure it in terms of nines, because when we cut this downtime to 0.01%, that would mean the uptime is actually 99.99%. This is how we measure availability. Availability is measured in terms of nines. So 2 nines is 99%, 3 nines is 99.9, 4 nines is 99.99, and of course we have 5 nines as well. Usually it maxes out at 5 nines because this is very, very good availability. In terms of a year, 99% availability, we know there's 365 days in a year, so 1% downtime would mean that our service is up 99% of the time, but it would be down 3.65 days out of the year. So 3.6 days, that's not very good. If you're designing Amazon.com, if the store is down 3.6 days a year, we're losing a lot of money. That's not very good, but 99.999% availability would mean that our service would actually only be down 5 minutes a year. So if we can get to this point, we're really not losing a lot of business. I mean, 5 minutes isn't very good. If we add another 9 here, we're taking this 5 minutes and dividing it by 10. So if we add another 9 here, we would actually be able to achieve 0.5 minutes, which I think is 30 seconds. So that would be even better. But you can see at this point, it's not a huge jump. I mean, 5 minutes down to 30 seconds, it's not huge. Like if we can get to this point, we're really, really solid. Availability is commonly used to define SLOs. SLO stands for service level objective. As developers and as designers of applications, we want to target something, aka an objective for our application to reach some availability requirement. And maybe we're designing some database, for example, and we want the availability of that database for users to be this. We want 5 nines of availability for our database. That would be a possible service level objective. As developers, we define that. Now, what's similar but slightly different is an SLA. You might see these two used interchangeably in industry, but SLA is technically different from SLO. You can think of an SLO as being a sub-portion of the SLA. So an SLA is actually an SLO plus some extra stuff. As AWS, we would define an SLA for our database. It would be the SLO, which is we want our database to have 5 nines of availability. That's the SLO. But as the SLA, we say that if we don't reach this level of availability, we will give you a partial refund. That's actually AWS's policy for AWS. If any of their services dip below their SLA, which is basically what they tell customers, this is what you can expect of our service, and this is what you're paying for. So if we don't reach this level of availability, we will give you a partial refund. That's kind of a customer agreement. SLA stands for service level agreement. It's not just a goal, it's an agreement with a customer that this is what you can expect or these will be the consequences. Now, a few more terms that you might be familiar with, but these have a lot of overlap. Systems can have reliability, fault tolerance, and redundancy, and these all contribute to each other. A lot of people even use these interchangeably. Technically, they have differences, but it's not super important to be always technically correct in a system design interview. But having a general understanding of these terms can be very important because these define how well our system can function and how we can avoid problems. If a user makes a request to our server and our server responds, that means our server was available, but that doesn't necessarily mean our server is reliable, because if we just have a single server like this, it's possible that the server could crash. So reliability is a different measurement, which is reliability is the probability that our system won't fail. Usually we don't have to represent this formally. Like we can't necessarily do a calculation that this server won't fail. Like we don't necessarily know the details of that. But generally speaking, we know if we just have a single server that's responding to users, we have a higher probability of failing than if we have 2 servers. So by adding a second server, we can increase the reliability of our system, but we're also increasing the availability of our system because, for example, if we just have a single server here, we could possibly have a lot of people making requests to a single server. We could even have, people maliciously trying to take our server down. You might have heard of this before because it actually happens a lot. It's called a DDoS attack, which is a denial of service attack or a distributed denial of service attack. That's when you have 2 Ds. If you just have 1 D, it's a denial of service. But basically, people could intentionally or unintentionally be making so many requests that our server is not able to handle all of them, which takes our server down. Maybe a portion of users will get a successful response, but most users are not able to access the server. This would be a problem. It could be that it's caused by the resources of our server. We could vertically scale this server. That would increase the availability because a higher percentage of users would be able to get a request a higher percentage of the time. time. So by vertically scaling our server, we can increase the availability. What about the reliability though? We still only have a single server. Maybe our server has to do like a Windows update or something. In that case, our server would go down. Maybe it just crashes. Maybe somebody unplugs the wire that it's hooked up to. The server goes down. In a case like this, we would really be happy if we had a second server, not just a single server with more resources. So this is why horizontal scaling can actually have benefits compared to vertical scaling. This is also called fault tolerance. If one portion of our system has a fault, then the system continues to operate successfully. This is fault tolerance. That means our system is tolerant to failures of portions of the system, but then the entire system continues functioning. One server goes down, but the second server still works, so it's still able to respond to users. You can see how fault tolerance is related to reliability. We would also call this redundancy. The English word redundant basically means unnecessary. We have something that's not necessary, so it's sort of a copy. In this context, it means we have a single server that's running our code. But then we create a second server that's running the exact same code. This server is redundant. We don't need it to respond to users because this server is capable of doing everything. These two servers are redundant for each other. We don't need both of them, but it helps to have both of them because in the event of a fault, in the event of a failure, we have multiple copies. So we can still do what we need to do. So our system can continue to function because we have a redundancy. By having redundancies in our system, we are able to have fault tolerance. That's the relationship. And with fault tolerance, we can provide higher reliability. It's not always 100% though, because if both of these servers are in the same data center, but maybe there's a hurricane and the data center power goes down, then both of these servers will go down. So it would be even better to have this server, this second server, in a different data center, maybe in a different part of the world, so that if one server has, some kind of natural disaster, the other one will continue to function. These are some of the high-level ideas that we're going to talk more about later in the course. Another really important measurement of a system is the throughput. Throughput in general means the amount of operations or data we can handle over some period of time. So in the context of communicating with a server, for example, a client or a user is making a request to a server and then getting some response back, we would measure the throughput of this in terms of requests per second. How many requests can our server handle per second? Obviously, this is helpful for telling us how many users, how many concurrent users could our system handle per second. Maybe a single server can only handle 100 requests per second. This is our peak traffic. 1,000 users is the peak that we need to handle. How could we modify the system to do better? Well, if we can horizontally scale this, well, maybe we can vertically scale this. Maybe we can just get a really, really good server. We can add some resources to our server here, and then we'll be able to handle 1,000 requests. This is definitely a lot easier. It's easier to design a system where we can just say, hey, just get a better computer. But we know that the downside of this is that there are limitations. We can't, infinitely vertically scale a single server. There are resources. We talked about Moore's law. And actually, there's another downside that we talked about, which is that this server is a single point of failure. If this server goes down, then our entire system goes down because this server is a single point of failure. We don't have redundancy. We don't have fault tolerance. The reliability of this system isn't great. It's pretty simple because we just have a single server. We don't have to worry about other things, but that's the downside. We could also horizontally scale this. We know a single server can handle 100 requests per second. So if we want 1,000, we can introduce 9 more servers here, and then we'll be able to handle as many users as, our peak traffic is. The downside of this though is that it can get complicated because we'll have to balance the requests between servers. We talked a bit about about how we can use a load balancer to achieve that. So then we have a lot more components in our system. So this increases the complexity, but we do have redundancy. And this is a more unlimited way of scaling. Horizontal scaling is less limited by physical resources, but it can definitely get more complicated, especially when you're talking about horizontally scaling a database, because then when you have data, you're distributing the data. Some of the data could be on, one area, and some of the data could be somewhere else. Having data that's distributed gets very complicated. So this is a downside that we have to account for as developers. Speaking of databases, when we're talking about how many requests a database can handle, we usually measure it in terms of queries per second, or QPS for short. And conceptually, it's very similar to servers. You could even call this requests per second. I don't think anyone would get mad at you if you did that. It's just more common for people to call it queries because that's the term used when you're talking about reading from a database. And databases have the same problems as servers that we talked about, where a single database can be a single point of failure. If we want to scale it, we can vertically scale it, but that has limitations. Horizontal scaling is better, but then we have data that is distributed, and that can get very, very complicated. Keeping data in multiple databases in sync, I'm sure you can imagine, is not super easy, especially when these databases might be on different sides of the world. What happens if one database is outdated compared to another database? These are problems that we'll be discussing later on. A third measurement of throughput that comes up is the amount of data per second, usually measured in bytes. It could be, gigabytes or megabytes or terabytes, but some amount of data per second. This is just a variation of requests per second or queries per second. When we're talking about how many users we want to be able to access our application, it makes more sense to measure it in terms of requests because each request is basically mapped to a single user. But if we're talking about some kind of data pipeline where we're given a bunch of data and we want to process that data into some other format, and it's not necessarily related to a single user or anything like that, designing a pipeline like this, it's much better to measure the throughput in terms of bytes per second because we don't even have a request. Maybe we just have a terabyte of data here. We want to transform that data into some other format and then write it to some, sync. It could be a database, it could be a server, it could be a file system, it could be anything. We want to know how much data can we process per second. If we had a terabyte of data and we're processing a gigabyte per second, a terabyte is 1,000 gigabytes, so we know it would take 1,000 seconds for us to do this. But if we started with 10 terabytes, then it would take us 10,000 seconds to do this. So that's why we measure throughput in terms of data per second. It can be useful in different contexts. But ultimately, throughput boils down to amount of operations or amount of data or amount of something over some period of time. Now, lastly, let's talk about latency, which can commonly be confused with throughput, but the difference is pretty simple. Throughput is the amount of operations or data divided by some period of time, but latency is just some period of time. So going back to our client server model, aka some user accessing our server, the latency of that would be the amount of time it takes for that operation to complete. So maybe it takes 1 second for the user to receive a response from our server. It's basically the end-to-end latency for the entire operation to complete. We could also measure the latency in terms of, how many seconds does it take for the request to reach the server, though that's less common because we care about the entire operation. We care about it from the user's perspective. So throughput in this context would be how many requests can our server handle per second. Maybe it's 10 requests per second. But latency is how long each individual request takes. Maybe one request takes 1 second to complete, but maybe another request took 2 seconds to complete. Latency could be caused by the network. Maybe a user is very far away from our server. Maybe they're on the other side of the world. So maybe for that user, it takes 2 seconds to get a response. But maybe for a user who's closer to the server, it just takes 1 second for that user to get a response. Now, if you recall, we actually already talked about latency when we looked at computer architecture, because latency is just the amount of time it takes takes for an operation to complete. It doesn't necessarily need to include a network, where a user is located somewhere else compared to the server. When we talked about how a CPU can read and write from RAM, we talked about it takes on the order, I believe, of microseconds to do something like that. But when it comes to reading from the cache, a CPU can actually read from the cache in terms of nanoseconds, which is an order of magnitude faster than reading from RAM. And the reason we have a cache is to lower the latency of individual operations, because if we can do that, then we can actually increase the overall throughput of the system. Our CPU can handle more operations per time if we can introduce something like this. And to lower the latency of a distributed system, we can actually do something similar. We could once again introduce a second server, and we could have these two servers on different sides of the world. Let's assume that this is our Earth. It's shaped like a peanut, I guess. But maybe we have one server on one half of the world and we have a second server on the other half of the world. Not only does this increase our availability and our reliability and increases the throughput, but it also reduces the latency for users located on different sides of the world. Without this server over here, users on this side would have higher latency than users on this side, but introducing a second server, we reduce the latency. Another technique for reducing latency is having a content delivery network, aka CDN, but we'll talk about that later in the course. The idea though is that we have intelligent ways of designing systems that can improve our measurements of our systems. I'm sure you can imagine that having multiple servers all around the world is a pretty common technique, especially because we just talked about how it improves latency, it improves throughput, it improves availability, reliability, it improves everything. So this is definitely going to be a technique that you're going to leverage in designing big systems. So I hope this lesson at least gives you a bit of background on what we're trying to achieve. We want to design powerful systems that can handle failures and handle high throughput and do it very efficiently with low latency. And we're going to spend the rest of the course expanding upon these terms and focusing on how we can satisfy these requirements.